question of how much math is used in environmental engineering is a common one. The answer is that math is a fundamental tool used every single day. It is not just about abstract theory from college courses. It is the language used to describe, predict, and solve real-world environmental problems. At its core, environmental engineering relies heavily on algebra, geometry, and trigonometry for daily tasks. Engineers constantly calculate flow rates in pipes, determine the volumes of treatment tanks or landfills, and figure out the correct dosage of chemicals for water purification. These are the foundational calculations that make projects work. Beyond the basics, calculus plays a critical role, particularly differential equations. These are used to model dynamic systems. For example, an engineer might use a differential equation to model how quickly a pollutant concentration decreases in a river after a spill. They also model the rate of contaminant decay in soil or the reaction kinetics inside a wastewater treatment bioreactor. You might not solve these by hand on a daily basis, but understanding them is crucial. Statistics and probability are arguably some of the most important math skills for an environmental engineer. Environmental data is inherently messy and variable. Water quality samples from a river will not be the same every day. Air pollution levels fluctuate. Engineers use statistics to analyze this data, to determine average pollutant levels, and to understand the range of variability. They use it to perform risk assessments, calculating the probability of negative health effects from exposure to a contaminant. Statistics also prove whether a remediation project is actually working. Furthermore, much of environmental engineering is applied physics and chemistry, which are both math-intensive. Fluid mechanics and hydraulics are used to design water distribution systems and manage stormwater runoff. This involves applying equations to calculate pressure, flow velocity, and energy loss in pipes and open channels. Chemistry principles, governed by mathematical relationships like stoichiometry, are used to design and operate water and air treatment systems. A core concept is the mass balance equation, which is a simple but powerful algebraic idea stating that what goes into a system must either come out or accumulate. This is used for everything from tracking pollutants in a lake to designing an air pollution control device. In the modern workplace, engineers rely heavily on computer software. Programs like ModFlow for groundwater modeling, GIS for spatial analysis, and even advanced spreadsheets perform the heavy computational lifting. However, this software does not eliminate the need for math skills. The engineer must understand the underlying mathematical principles, like the differential equations or statistical models the software is using. This understanding is essential to set up the model correctly, to interpret the results intelligently, and to know when the computer's output doesn't make sense. Without a solid grasp of the math, the software is just a black box, and its results can be dangerously misleading. So, while you may not be integrating complex functions by hand every day, a strong conceptual and practical understanding of calculus, statistics, algebra, and the math behind fluid mechanics and chemistry is absolutely essential to be a competent and effective environmental engineer. Thank you for watching. If you found this helpful, please like and subscribe for more content.